So here's what we're going to do. We're going to do a little bit of reasoning about what we'd expect. Remember those curves you saw? We'll come back to them. What we'd expect for the specific heat capacity of aluminum versus lead. So we have two blocks, an aluminum block and a lead block. And the aluminum block has a mole of aluminum atoms and the lead block has a mole of lead atoms. So roughly, approximately, which picture looks right? There. Well, think about what you know about. So same number of atoms, 1 mole, right? Okay, so that means nobody wants the aluminum block to be bigger than the lead block, but some people think they'd be roughly the same, and some think the lead is bigger. Now, a lead atom is a lot more massive, right? But how much bigger is the interatomic bond length? Which means how much bigger is the diameter of a lead atom than the diameter of an aluminum atom? Is it a factor of what that looks like, a factor of 2 or 3? They're not that different. The sizes of the atoms, the interatomic, atomic radii are really just not that different. So the big difference is you find these two, so they're approximately the same size. They're closer to the same size than they are wildly different. But the big difference is you pick up the aluminum block and it's easy, and you try to pick up the lead block and you notice that so the density is much greater, certainly. Okay, so they're roughly the same size, same number of atoms. Here's what we're going to do. We're going to imagine taking them both down to almost absolute zero. You can't quite get there, but close as we can. So they're really, really cold. And then we'll add 1 joule of energy to each block. And so we're going to think about, at this low temperature, what we want to end up predicting is which one of them should have the bigger specific heat capacity here. So we're going to put 1 joule of energy in each block. Now, 1 joule of energy isn't the same number of quanta for aluminum and lead. So remember that the energy of 1 quantum has in it this quantity, the square root of the interatomic spring stiffness divided by the mass of an atom. So one of these diagrams shows the energy level spacing for aluminum, and one of them shows it for lead. Which is which? Which has the bigger energy level spacing? You probably don't really need to do a calculation, because the spring stiffness, interatomic spring stiffness, is the Young's modulus measurements are given here. It's 16 newtons per meter for aluminum and 5 for lead. The mass of aluminum the molar mass of aluminum is 27 grams, and the molar mass of lead is 200 grams. Okay, so which one has bigger energy level spacing? Okay, big vote for A being aluminum. That says that 1 quantum of aluminum is more joules than 1 quantum of energy for lead. And so you're saying basically that that 16 divided by 0.027 is going to be a bigger number than 5 divided by 0.2, what was it, 207? So a big number divided by a small number is bigger than a small number divided by a big number. Right. So it looks like 1 quantum of energy for aluminum is just a lot more energy than it is for lead. Well, yeah, but it's going to be in both places, right? So all we're interested in is relative magnitudes. We're not, yes. Okay, so levels spaced widely for aluminum, narrow for lead. So maybe we should put this on the board. So the next question is the next step in our chain of reasoning. So we have we decided that that was aluminum and that was lead. So the next step is we put 1 joule into each block. Which block got more quanta? Yeah, so we end up with more these closely spaced levels. 1 joule is just a lot more quanta, a lot more levels than it is here. So we put 1 joule in and we've ended up adding a lot more quanta for lead. Okay, we don't need a clicker question. Number of oscillators in each block. They're the same, aren't they? Because we got the same number of atoms, so that's cool. So therefore, by putting 1 joule, with 1 joule of energy added to each one, which one's going to have greater number of ways of arranging the energy? Wow. Okay. So there's just plain more ways of arranging the energy because it's more quanta, so you can shuffle it around more. All right. So if there are more ways of arranging the energy in the lead, which block has the greater entropy now? Okay, greater entropy for lead. And so, the initial entropy was 0 because we hadn't added any energy, right? So here we go. The lead block has greater entropy, so which block had a greater delta S? That is a first. Wow. All right. See, it was worth coming to class today just for that. Which block has the higher temperature? You have to think about this one. This one is not the same as the previous 3 questions, okay? So okay, well, that's correct. So if you have, for aluminum, you have a bigger delta S. I'm sorry, lead has a bigger delta S, sorry. Same delta E, 1 joule. So if that means 1 over T was bigger for lead, which means the aluminum is hotter. Okay, so we put in 1 joule, and that made the aluminum block get hotter than the lead block. So which one at this very low temperature, which one has the higher heat capacity? So the temperature changed, the final temperature of the aluminum was greater. You put in 1 joule, the temperature of the aluminum increased more than the temperature of the lead. So the change in temperature for the aluminum was greater. Okay, so higher temperature, so bigger delta T, same delta E. So that's a smaller heat capacity. So in fact, you had to put, okay, so you said lead was greater. Here are these data we just looked at. Here are these data that's the same data we were looking at with the VPython program. The The gray circles are aluminum. The black dots are lead. We're talking about low temperature here. And so at a low temperature, it's true that the specific heat capacity on a per atom basis is actually bigger for lead. So you could have predicted it.